Hello, everyone, and welcome to the live session for today. What is this? May 21st. We are very excited to have you here with us. We are just wrapping up our own school year here at the university, and we are looking forward to our summer, and we're looking forward to answering your questions about astronomy. My name's Matthew. I work on the online classes that we have available, and I do a lot of behind the scenes stuff here. I'm part of the astronomy teaching staff. And just a real quick welcome for those of you who have not been with us before. I'll go over the way that this works. Please post your questions in the chat. I will grab those questions from there. I try to go in order generally, but I do jump around sometimes to get a variety of questions and to give more people an opportunity to have their questions answered. Please post your questions only once. I promise we see those in the chat. Like I said, sometimes we just jump around to get a variety of topics. We also keep this at a beginner level. So if you have really advanced questions, this is not quite the right forum for that. So keep those questions at an introductory beginner level so that we can all enjoy and appreciate the stream. I'm going to hand this over to Chris to welcome everyone, and then we will get started with your questions from the chat. Go ahead, Chris.
Okay, yeah, welcome to everyone who's found us through being in the online classes, or just you've stumbled upon us on the internet, which is great. So I often start with a news story. I'm going to start with a comment or an update, if you like, on some of the things that have been going on in the federal funding of science. It's not specific to astronomy, but the National Science Foundation is a core part of how astronomy research in the United States works. I've had NSF grants for research for decades, and most of my colleagues in the department also do for their research on any topic. And NSF is the prime funder of astronomy research. It funds facilities, it funds individual faculty members and researchers, it funds graduate fellowships. It's central to astronomy research in this country. And it's under assault. It's being eviscerated, essentially. The update is that even if Congress pushes back on a president's budget that proposes to cut it by 50%, which essentially would kill it. I mean, scientific research as we understand it in the US would die on the vine if the federal agencies that support it were cut by that much. So even if somehow Congress manages to push back, which some people don't have much confidence of, all the changes are already happening. So the NSF, so that everyone knows, only 10% of its budget goes to the staff, the people who work there, civil servants and rotators, who are visiting academics who help with proposals. 90% of the budget just goes out the door. It's grants that go around the country to every state, red states and blue states. And so it's a pretty efficient agency. There's no fraud, waste in the NSF, essentially. That anyone who says that is just blowing smoke. So they've cut the civil servants by a significant amount. That happened a few months ago. They've consolidated the 35 different programs within the NSF into 5 large categories. They've declared this, they being the administration, have declared that the NSF's core mission should be to support only 5 science areas, including some worthy ones like artificial intelligence, but excluding essentially 80 or 90% of what the NSF historically has done across the life sciences, the physical sciences, geoscience, climate science, and so on. So the broad portfolio that the NSF has always had for decades is in danger of being shrunk to a highly targeted core. Education programs will be almost completely killed. That's the same thing that's happening within NASA, and that's a lot of our funding historically has been from the education side. So it is a dramatic change. They're also planning on cutting the number of rotators, as they're called, by 80%. Rotators are visiting staff because the civil service complement in NSF is quite small, very lean and efficient. And so they get most of their proposals reviewed, and a lot of their programs really bolstered and supported by these visiting academics who come in for 2 or 3 years and live in Washington and work at the agency and do an enormous amount of work for the agency. It's a bulk of their work. It happens from these program rotators. And by cutting that program by 80%, they're essentially guaranteeing that agencies will grind to a halt. All of this is happening right now. The administration also capped NSF's overhead rate, the amount they give universities to pay for the research, because it has to be funded in labs. Labs have to be staffed. Electricity has to be supplied, etc. It's not waste. It's not fraud. They cut that arbitrarily from the typically 40 or 50% universities have typically charged for decades to 15%. That's been contested in court and is on a hold. All of this amounts to a full frontal assault on the premier science funding agency of the United States. I don't have any happy news to report on that front. It's a siege mentality at this point for many scientists working in this country. And I will give updates as they come.
All right, thank you very much for that update, Chris. We're going to turn to some questions, and if people have questions specifically related to that, please post those in the chat and we will get to them. The first question is from Neil Thompson, who's on with us live, who asks, hi, can you please discuss the latest thinking on black hole soft hair, if it does exist? Could it carry polarization information, and if so, what would that polarized state tell us?
So the idea of black holes in hair, it's a strange term, of course, doesn't sound very physics-like. It goes back some decades when people were arguing about what the nature of the event horizon was, and going back to Stephen Hawking's seminal work in the 70s and 80s, and Roger Penrose, they actually had a theorem called the no-hair theorem, which said that black holes did not have anything surrounding them. There was no ergosphere or chromosphere or external region around the event horizon that had any meaningful structure or information. And that's been softened over the years, and people have wondered whether black holes might have hair, which is to say external regions that could potentially code information or be vehicles for entanglement, for example, between particles inside the event horizon and outside. There are all sorts of exotic potential mechanisms. As far as I can tell, all these, including the soft hair idea, which had received some theoretical attention, are all in the realm of pure speculation. None has had an observational test that I am aware of. And that's the problem with black hole physics at this point. The theory is quite advanced and sophisticated, but the nature of the effects that are being sought are quite subtle, and observations of black holes are quite difficult. And so testing these theories so far has not been possible.
The next question, I'll skip to this one because it's related to black holes. Justin Pro Gaming would like to know if you can talk a little bit about white holes. What are they? What do we know about them, and where do they fit in?
Yeah, we get this question periodically. White holes are a theoretical construct of the potential for example, a black hole to be paired with a white hole where there's an interconnected region of space-time and the matter goes in irretrievably in one side, the black hole with its event horizon, and then emerges as energy and particles on the other side. So it's a rupture in space-time, essentially. So it's a theoretical concept that fits within the framework of general relativity, so it does not violate the laws of physics as we understand them. But it assumes a structure of space-time that's complicated enough to lead to the possibility of a white hole, of interconnected regions that are disparate in space and time. And the universe we live in shows no signs of being structured that way. Space-time is extraordinarily simple and flat and kind of boring, except for those very small regions where a black hole has sort of excised a part of space to be invisible from us. So at this point, and for the last few decades, white holes have remained in the theoretical category. It's also hard to know how you would actually observe a white hole, because there are many sources of energy and radiation and particles in the universe, and distinguishing something that's just an energetic phenomenon from a white hole is observationally quite challenging.
The next question is from Monty Roeder, who's on with us live, and asks, given the distance involved and the enormous technical issues that would have to be solved, do you think it will be possible to get to Mars and be able to actually get a colony of any sort started?
I think the colony on Mars idea, which has floated a lot, and Elon Musk has staked his reputation and a good part of his company on that plan, is very much embellished to the point of over-optimism. My best guess is that just getting humans to Mars is not going to happen within the next decade. It might happen by the end of the 2020s, but probably early in the 2030s. And a colony on Mars is decades away after that. The logistic and energy considerations are formidable. It's a long trip. You need to bring with you fuel. You have to have living capacity for a small set of humans. Even if the first colony is very limited and gets resupplied by the Earth, it's going to have a sufficient diversity of talent and expertise and redundancy of personnel that if people get sick or injured or whatever, that you can still function. So it's unlikely you can do this as we did on the moon by having a short visit with 3 astronauts. This will probably have to be 6 or 10 at a minimum, and a viable colony, of course, would need 100 or 150 people. That would be a self-contained one. And people have costed this out, and they've worked out the logistics, and you shouldn't believe anything you read which claims this is going to happen within a decade or even 15 years, because the costs and the complexity of such a thing are enormous.
Thank you very much, Chris. The next question is from N, who is on with us live, who asks, I just finished my first research on gravitational lensing and how black holes bend light. Can you talk a little bit about what we have learned from gravitational waves? This is also from Ben Tennyson. So what do we know about gravitational waves? What have we learned about the universe from gravitational waves?
So rewind that question, because it started to be about lensing and then became about waves. Which is it? Which is the question about?
Oh, I'm sorry. I apologize. You're right. I shifted. The question is gravitational lensing and how black holes bend light. Can you talk a little bit about gravitational lensing and what we know about it and some recent discoveries related to gravitational lensing? Thank you.
Right. Gravitational lensing is a core prediction of general relativity. It was put out as a prediction soon after Einstein published the theory. So I think the first paper talking about it was 1919. It was then clearly predicted by astronomers in the 1930s, but lensing was not observed until the double quasar, a mirage essentially of a single quasar looking like 2, was discovered in 1979 at Mount Hopkins in Arizona, one of our observatories, and by colleagues that I know well. Since then, lensing has been found in many places. Quasars can be lensed, galaxies can be lensed. Hubble has had beautiful pictures that you can download from their public website of arcs of galaxies that are lensed by an intervening cluster. And the short story, because this is a huge field of astronomy, is that lensing has affirmed that most of the universe is made of dark matter as opposed to the visible stuff we're made of. And this is ignoring dark energy for a minute. So lensing is an affirmation because mass bends light whether it emits light or interacts with light or not. So dark matter is measured, is probed, is weighed by lensing. And it's been the most successful way to track dark matter in the universe on different scales. That's probably, in the simple terms, the best success of lensing over the past few decades.
The next question is from Sharvan Kumar, who sent an email and says, actually, my younger brother asked me a question, and I was wondering if you can talk about this. Why does the Earth rotate about its axis, and why is it tilted by 23.5 degrees? Is there a specific reason for the tilt?
The spin of the Earth around its axis reflects angular momentum, which in turn reflects the angular momentum of the cloud of gas and dust out of which the Earth formed when the Sun formed 4.54 billion years ago. So the Sun has most of the mass of the solar system, and the angular momentum of the Sun is determined by its rotation, spinning about once a day. And the Earth's spin axis and vector and angular momentum vector are aligned with the solar system. So not unreasonably, in the gas of cloud and dust that was rotating, that formed the rotating Sun, the Earth formed as a rotating object. And that's true of all the planets except Venus, which is the oddball exception, spinning the other way. The tilt of the Earth's axis could come by any number of means, and typically it's just by interactions with other planets over time. Um, the axis of planets orbiting the sun are all tilted by some degree. The massive giant planets are only tilted by a few degrees. Mars is tilted by about the same amount as the Earth. So it's not unusual to have an orbital tilt, and it's caused typically by instabilities or interactions in the long period of time the planets have been orbiting the sun. In the case of the Earth, the axial tilt is very stable over long periods of time because that's from the moon interaction. Mars is an interesting counterexample because Mars' orbital tilt, which is similar to that of the Earth, varies much more widely. It ranges from 20 degrees to 45 degrees because Mars is not stabilized by any moons. It has two very small moons. So orbital tilt does happen naturally either in the formation process or by interactions after formation.
The next question is finally from Ben Tennyson, who has a question about gravitational waves. I hope you're doing well, and I want to know what we have learned from gravitational waves and observing those.
Gravitational waves came into their prime in 2016 with the LIGO instrument, situated in two independent and identical instruments, one in Louisiana and the other in Washington State. And the collaboration of hundreds of scientists has been extremely successful since that first detection. So there have been now hundreds of gravitational wave events, and through them we've learned an enormous amount about black hole mergers, neutron star mergers, black hole neutron star mergers, and these kind of collisions and interactions of very dense, compact objects. And this has allowed us to test general relativity in new ways. So it's the most powerful success of gravitational waves so far.
The next question is from Nancy, who's on with us live. There is astronomy, astrophysics, and astrobiology. Then why not astrochemistry? Can you please give an introduction as to if there is such a thing as astrochemistry and what is it all about?
Yes, there definitely is astrochemistry. So it's a hybrid field, which is at the interface of astronomy and chemistry, because the universe, most of the universe is actually low density and quite cold, especially in solar systems and star forming regions, and it's very amenable to the formation of molecules. I think at this point over 200 different molecules have been detected in interstellar space, which is an enormous number, ranging up to 12, 13, maybe 14 atoms in them, so quite complex molecules. And so astrochemistry is a huge field. The nature of molecules has a large impact on how stars form and planets form, because the molecules often act to cool the gas and facilitate the collapse of a gas cloud. The molecules, of course, are interesting in terms of looking for the precursors of life. So do the building blocks of life, like amino acids, exist out in space? And the answer is yes, they do. So astrochemistry is important as a sort of lead into astrobiology. And as a discipline, it's a significant discipline. They have conferences on astrochemistry. In our faculty of about 35 professors, we have 2 that are astrochemistry experts, and that's their field. There are journals that publish astrochemistry, although a lot of these articles appear in general astronomy journals. So it is a niche or a subfield of astronomy, but it's a very active niche. Most of the observations, and it's a mixture of theoretical work, also laboratory work. So this is one of the areas where you can actually simulate the nature of molecules in space in the lab and understand them that way. And experimentally, it's typically done with radio or infrared telescopes because molecules have vibration states and energy transitions that happen at very low energies or long wavelengths. So it's really radio or millimeter astronomy that lets us observe molecules in space.
The next question is from an email. I wanted to ask about the latest discovery or claims about detecting DMS, which is dimethyl sulfide, I believe, on exoplanet K2-18b. Is it really possible to detect such a compound from 124 light years away with present instruments? Can you please clarify how this was detected and whether this is a legitimate finding.
So there's been a real controversy over the claim of dimethyl sulfide as a biomarker, as a potential indication of life from the atmosphere of one of these Kepler exoplanets. So just to concentrate on the molecule itself, the detection of dimethyl sulfide is not clear-cut. It's based on James Webb Space Telescope spectroscopy in the infrared, near infrared. And there is a weak feature in the atmosphere of this planet at a wavelength associated with dimethyl sulfide as a molecule. The trouble is you don't know a priori what the atmosphere of this planet contains, and it could contain many molecules, many different molecules, and some of them will have spectral transitions in the same range. So just seeing a transition at a wavelength that matches a dimethyl sulfide transition doesn't prove that it's dimethyl sulfide. It could be something else. You could be confused by something else. In this case, the bigger issue is the weakness of the detection. It does not reach the gold standard of 5 sigma, where the odds of it occurring by chance or due to noise or something in the detector are infinitesimally small. It's a very weak detection, so it needs to be followed up. Also, the claim that it's a biomarker is not completely convincing either. Indeed, on the Earth, dimethyl sulfide is associated with life in the ocean, phytoplankton typically, but not exclusively. Dimethyl sulfide is seen in interstellar space, in star-forming regions, and so it's seen in places where there's not necessarily any biology at all. So that means it's not 100% clear that it's a biomarker. So all of these things put together mean most of the community is still remaining very skeptical of this claimed detection of life due to this molecule.
Thank you. The next question is from Johan Garcia, who has sort of a related question. What are the current criteria for space telescope sensors to detect life based on gases found in the atmosphere of exoplanets?
Well, the criteria are difficult to completely specify, and I'll get to the reason in a minute. But typically, biosignatures or biomarkers are gases in the atmosphere of a planet that could not be produced by geological processes or simple atmospheric physics. They have to be caused by biology. On the Earth, oxygen is the classic biosignature, and it's relative ozone, which also exists in our atmosphere, because that oxygen was created by microbes several billion years ago. There's no question that that's how it originated. So seeing a large fraction of free oxygen in an atmosphere is probably a good indication of life. But other biomarkers would include methane, for example, because a significant fraction of the free methane at a much lower percentage level on Earth is caused by biology. And then there are other things that could arise. So it's not a single molecule, it'll be a set of molecules. And then the larger problem that I alluded to, is the fact that this all assumes we know the nature of biology beyond Earth. If biology has a different metabolic basis or a different chemical basis, then the biomarkers could be molecules we're just not looking for or not familiar to us from terrestrial life. And that's a big issue because we don't know how strange life could be out in the universe, and that in turn means we don't know exactly how to look for it.
That is an excellent lead-in to our next series of questions. A related question is from one of our live participants: what would be the primitive biochemical pathway within a cell for it to be determined as a living organism? I mean, how would we find life and determine that a cell is actively a cell?
So astronomy is not able to scrutinize the many exoplanets that have been found at the level of determining the nature of life on them. When we look for biosignatures or biomarkers, we're looking for the global atmospheric alteration caused by biology. So it's a totally global effect caused by microbes, but by a whole planet's worth of microbes. So there's nothing in the toolkit of astronomy that lets us diagnose cells or the nature of the cells. That's just far beyond what astronomy can do. Cells are, of course, tiny things anyway, so how could we possibly see them on a distant exoplanet? We might, if we see biosignatures and believe their detection, be able to infer the metabolism that led to those gases or molecules, and that might let us sort of work backwards towards what the cell type might be. But that's a very uncertain process. So I think the simple answer is we're not anywhere near being able to talk about the cellular basis of life beyond Earth.
And then another related question from Ben, who's on with us live. Life can potentially have different kinds of metabolism. Um, does NASA and others, or do NASA and others, have a way of thinking about this as they actively search for another kind of life?
It's very hard to think out of the box on this. NASA, as the agency that designs missions to do this, is in a bit of a quandary on that, because you're spending, first of all, hundreds of millions or billions of dollars on a life detection experiment or a sophisticated rover that might detect life. And with that investment, you need an answer. And so when you need an answer, you have to frame a scientific question that's quite focused. And so you, of course, will therefore start by looking for life as we know it and look for the markers of terrestrial life. And then at least you can answer the question, given the investment. If you don't know what life is, then it becomes very hard to design an experiment. So if you can't frame a particularly focused question because you don't know the nature, the diversity of possible life beyond Earth and its metabolism, then you can't frame a scientific experiment, so you can't ask the question. And that's the catch-22 that NASA finds itself in. And they've, of course, veered towards asking the question about life as we know it. There is a claim that even the Viking experiments, which were the first 1970 situated on Mars, the first experiment, 4 different experiments to look for biology on Mars by reacting chemicals with the soil and seeing if anything grew or anything happened. There was a claim that at least one experiment, the wolf trap experiment, detected life that might have a different metabolic basis than life on Earth. But the result was indeterminate. That was a technology from 50 years ago, so we would have to do the experiment again. So this is actually a big conundrum in the search for life beyond Earth.
The next question is from Ernest Stalder, who's on with us live. Good morning, Professor. I know that supermassive black holes exist in most galaxies, but have intermediate-sized black holes been discovered? If so, when and where?
Yes, it's a very interesting and active field to look for intermediate mass black holes. So what do we mean? Well, the most massive black holes that result from the death of stars are probably up to, as we know, they're a bit more massive than we expected theoretically, and we know this from LIGO's detection of black hole mergers. So we know that dead star black holes go up to about 30 or 40 times the mass of the sun. That's as big as you can get. And then if we go down from the most massive galaxies, a galaxy like the Milky Way has one of the more modest black holes, 4 million times the mass of the sun. So that's a big gap. And what is filling the gap? Well, a small, relatively small number of secure detections of intermediate mass black holes have been found. And not surprisingly, one of the best places to look is globular clusters, because globular clusters are aggregations of hundreds of thousands or a few million stars, so 1,000 times fewer stars than a galaxy. And indeed, the black holes that are found in globular clusters have masses of 1,000 or a few thousand or 10,000 times the mass of the sun. So they neatly fill in part of that gap. And we do think that nature is able to make black holes of all different masses. You just need a situation where there's enough gravity in the smaller object to make one of those smaller black holes. And they're hard to detect. They're typically found through X-ray emission.
Our next question is from an email from Wendy, who asks, based on JWST data that big galaxies develop faster than thought possible, some cosmologists propose that the universe could be different ages in different places. What are your thoughts on this?
Yeah, I think that's a stretch. I think the discovery that large, massive galaxies form quickly is secure. I mean, we've seen high redshift galaxies at redshifts of 10 or 12 or 14, which is within the first half billion years of the universe, that are larger than most models would expect. But that doesn't break the model. It doesn't break cosmology, because you're allowed to have rare, high density, high overdensity peaks in the evolving mass distribution that lead to large galaxies, as long as they're not too common, and in this case they're not. As for this varying with distance, with the location in the universe, there's no indication of that. Foundational to cosmology is the cosmological principle, which is that the universe is isotropic and homogeneous, and there's nothing special about any particular direction in space. And I don't think anything in the high galaxy redshift work has violated the cosmological principle.
The next question is from Hillary Wilkinson, who's on with us live. Could you share any interesting developments, if any, on the topic of the simulation hypothesis?
The simulation hypothesis generates a continuing small amount of interest. Of course, it peaked 10, 15 years ago with the work of Nick Bostrom in particular, who not only wrote technical articles, but popular articles that got a lot of traction. There's no real progress on the hypothesis because, of course, verifying the hypothesis is something we're not really able to do. So the theorists and the logicians and the philosophers have pretty much weighed in on every aspect of it. And I see a scattering of papers every now and then on the simulation hypothesis, but they're basically just looking at detailed implications. There's no new foundational research on it because you'd actually have to come up with a way of either verifying or negating the hypothesis. And almost by construction, it's a very hard hypothesis to negate.
The next question is from Ben, who is on with us live. Hello, Professor. What subfields of astronomy would you recommend for incoming students to focus on in the next decade for the largest impact?
Well, astrobiology, which is almost its own field now, but it is the subfield of astronomy, is obviously going to stay hot and active. The peak of exoplanet detection, it probably happened during the Kepler satellite, so the rate of discovery of exoplanets has cooled off a little bit, but the follow-up work on characterizing them and understanding them and finding the first signatures of life, that's all up ahead and not far ahead either. So that's the most obvious field to pay attention to and to go into. Cosmology will continue to stay hot also because dark energy and dark matter, the two main ingredients of the universe, we don't know what they are fundamentally. So new experiments, new data will come into being, typically based on large surveys, that will try and answer these foundational questions. So those are the two areas which are very active and hot right now and which are likely to stay that way in the next decade.
The next question is from Lawrence K. Does an observer positioned locally around a black hole outside the event horizon observe Hawking radiation? Or is Hawking radiation only detectable by a distant observer?
No, anyone or any probe or anything beyond the event horizon could in principle detect Hawking radiation, which is emitted through an interaction of pair creation from the vacuum at the event horizon where energy escapes or particles escape. So you don't have to be far away, you could be nearby. The problem is the rate of Hawking emission and its equivalent temperature, which is like a few billionth of a degree Kelvin, is so low, it's so subtle that no observation has been designed yet that we think can succeed in detecting it.
The next question is from David Gold, who's on with us live. What is the best theory for the moon of Uranus, called Miranda, to have such a deformed Frankenstein's monster-like surface?
When moons have fractured or chaotic surfaces, the typical thing, what's typically invoked is collisions. So all the giant planets have big moon systems, 100 or more for Jupiter and Saturn and dozens for Uranus and Neptune. And in the formation phase, there were probably more moons, and moons collided and some merged and some shattered. And so some of the peculiarities of individual moons, like Miranda, can be attributed to an early interaction or collision. That's very hard to prove, of course, because the evidence is long gone. These interactions and that events that cause that peculiarity have disappeared because they happened billions of years ago. The only other thing that can make a moon peculiar is internal geological activity. So if the moon is massive enough to have some level of volcanism, perhaps enhanced by tidal heating from the parent planet, then you can terraform the planet. You can have lava pouring over it. You can have ice and rock mixing and melting and remelting. That's not necessarily clear for Miranda because it's not quite massive enough for that to work effectively.
The next question is from Jamal Barghouti, who asks, is the universe expanding? If so, what is it expanding into? A balloon expands to fill out a room that already exists.
Right. Yeah, the universe is expanding. The evidence for that came from Edwin Hubble in 1929, first observing the redshift of galaxies and showing that there was a linear correlation between the galaxy redshift, or recession velocity, and distance of the galaxy. And that is most easily interpreted as a universal cosmic expansion. In the Big Bang cosmology, the expansion does not have to take place into anything at all, because the universe is a self-contained system of space and time that started 13.8 billion years ago. And if you want to think of it some way, you can think that space and time unfolded from the singularity of the Big Bang to the current large, flat, old, and cold universe we live in. So the analogy with a balloon breaks down at that point, and it's not useful.
The next question is from Thelia Smith, who's on with us live, and asks, can you please discuss some of the theories or ideas about the end of the universe?
Yes, the ideas of how the universe ends have been around for a while. They're based on physics, and the physics is not complete because we don't have a complete theory of all parts of physics, and the gravity theory in particular is unlikely to be the last word, general relativity. So, given our uncertainties of physics, the ends of the universe typically involve the death of all stars. So the luminous era of the universe, where stars within galaxies are shining, that will end after about 1 trillion years with no new gas left to form new stars. And so that will be forever a dark universe. That's the first phase of death. The second phase of the death is sort of the evaporation by sort of a means of gravitational interactions, where gravitationally bound systems like solar systems or galaxies themselves will gradually evaporate, which is to say objects that are bound within them by gravity will gradually move into interstellar or intergalactic space. And so structures like galaxies and solar systems will evaporate or dissipate. And that time scale is trillions to maybe trillions of years. To go beyond that, you need particle physics, because the best theories of unification suggest the proton is not stable, therefore normal matter is not stable. And that suggests that on the very longest time scales, normal matter will decay. And the end point of that, and if you play it out, and we haven't seen proton decay, so that's a speculation, would be a universe filled with neutrinos, antineutrinos, positrons, electrons, and very low energy photons. And that's a sort of called the heat death of the universe.
The next question is from a couple of our live participants, and we take these every once in a while. The specific question is that if someone wants to be your student, how do they come work for you? But more generally, how do people find professors or mentors to work with as undergraduate or graduate students?
So for me, it's the same as for all my colleagues and at other universities. Universities have really great difficulty employing outside people. So you can't really work with a faculty member and do research unless you're enrolled as a student of some kind, undergraduate or graduate. For example, I mean, we have very smart high school students in Tucson, and other universities have them in their local neighborhoods and communities. It's very difficult to hire high school students within a university. I mean, that's partly because if they're under 18, there are various restrictions, but it's mostly because they're not university employees in any way. So it typically starts by being a student within the university. And once you're within a university as an undergraduate, you have a major, or even if you're undecided about your major, you can go to advisors in the department whose research you're interested in, like astronomy, and just ask what faculty members are working with students. Our faculty advisors keep lists of projects submitted by individual faculty and the types of students they might be willing to work with, and whether they can pay those students or give those students study credit for working with them, or whether it's purely volunteer work. And that's a mechanism that's common to all universities. That's undergraduates. For graduate students, it's a little different because graduate students apply very specifically to programs in their field. And so our graduate students apply to our astronomy program. And if they're admitted, they have free choice to work with whoever they want among the faculty. Many grad students on their initial visit, make connections or talk to faculty, and often have lined up a mentor before they even arrive when they're admitted. But other students wait till they come here to talk to people and then take their first semester to see the lay of the land and connect with an advisor. So for graduate students, it's a more targeted thing because you have to apply to specific programs. And then when you're within a program, you explore the range of options among the faculty in that program.
The next question is from an email from Kathy Donnelly, who is taking the History and Philosophy of Astronomy course, and they just finished the timekeeping lecture. I understand that a main impetus in developing more accurate timekeeping was to improve navigation. I'm wondering if you have any insight into why Europeans had so much difficulty navigating, while it seems like the ancient Polynesians were able to navigate the Pacific and find islands without these elaborate timekeeping devices.
That's a good question because Pacific navigation, as we now understand it, was quite sophisticated. It wasn't highly precise, however. The celestial navigation using positions of the stars was able to navigate distances of thousands of miles with an error of tens of miles, perhaps. And that's good enough if you're traveling a large distance to spot an island chain like the Hawaiian island chain, for example, at a distance. So you don't have to be super precise in your navigation. So it was reliable, it was sophisticated, but it wasn't super precise. Now, when you play that into the realm of commerce and shipping, the precision that the Polynesians, for example, used would not be sufficient. Because if you're navigating coastal regions with that uncertainty, you're quite likely to run aground, or in an area where there are coral reefs, you'll run into a coral reef. So the navigation requirements for trade in Europe at the time, in the 17th and 16th century, were more stringent than for the Polynesians and the Pacific Islanders. And that it was the great naval disaster, I think in 1707, where many people were killed and ships were destroyed, that led to the urgency of developing accurate timekeeping.
The next question is from one of our live participants. Jamal asks, the universe has billions of galaxies. If the Earth is the only planet that has life, it cannot be a random occurrence, it seems to me, in view of all that exists. What's your response to the idea that an intelligent designer must therefore exist?
It's an interesting idea, but I think it's logically flawed to draw that conclusion. So let's just examine the premise. First, the premise that life is unique to the Earth, that's just a premise that has to be verified by observation. So we're actively trying to find life beyond Earth. And even if it's hard and may take a while, I don't think we'll have the answer to that question for a decade or more. So we're not yet allowed to say that life on Earth is unique and therefore is a fluke or must be caused by an intelligent designer. So that's drawing an inference that you're not allowed to draw at this point because we simply don't know enough about the prevalence of life beyond Earth.
The next question is related to the topic you brought up of the National Science Foundation at the beginning of our live session. N says, so going off what you said about the NSF, what would that mean for the ongoing projects? Would they pause or continue with grants they have?
It's very difficult. It's very personal. Matthew and I, we have a proposal submitted to NSF a few months ago that's been on complete hold because education part of NSF is not reviewing grants, basically. And we're almost certain not to get the grant anyway because we're studying misinformation and the administration has chosen to kill within the NSF any grant dealing with misinformation or disinformation, because in their perception, false, I think, and many people think, that kind of research is being used to suppress right-wing speech. That's just simply not the case, because research on scientific misinformation has nothing to do with politics. So that's unfortunate. So we know that grants are being canceled. We know that grants are on hold. We know that it's affected students' funding. It affects faculty funding. We're having to bridge some students over the summer. We're having to scramble to find money for faculty salaries for the summer. So NSF is barely functioning as an agency right now. And it's not clear how or when that might change. And the killing of grants is not exclusively along the DEI realm, which has been the most publicized aspect of grants being cut. As I said, it also happens for research on misinformation or disinformation. And then the scope of NSF's portfolio is possibly going to shrink dramatically, which would lead to loss of other grants. Another immediate impact on us here at Steward Observatory is that we've been seeking approval from the NSF to go to the full construction phase of the Giant Magellan Telescope. So we submitted our design review, and it passed muster with an external advisory committee. And it's basically up to the National Science Foundation to, it might cost $100 million to go to that next phase, and we think we can raise that privately. So all they need to do is give the green light, just an administrative decision. And the NSF director resigned without making that decision. The new director does not seem inclined to make that decision. So we have a major roadblock in the Giant Magellan Telescope development. So there are big capital projects that are totally in trouble or having problems, as well as the grants of individual researchers like me.
The next question is related a bit. Hernan Reyes sent an email. I read on space.com in the news today that the Mars Sample Return Mission, or MSR, which was supposed to bring back samples of Mars turf, has been tagged as grossly over budget and whose goals would be achieved by human missions to Mars. And my question is, what are your thoughts on that? Doesn't it seem like the Mars sample return was supposed to prepare the way for humans on Mars? What are your opinions on this sort of robotic versus human mission, and whether this is a short-sighted change?
Yeah, I mean, so the verdict is not completely in yet, but it is very likely that under the new administration, Mars sample return will be canceled and will not happen. That's amazing and crazy. The rovers have been caching samples, dozens of samples already. There's a pretty advanced plan to bring them back. So all this advanced work that's already been done to scout out the best samples and secure them in vacuum tubes and stage them in places where a future mission can pick them up and return them to Earth, that's already been done. And there's already been a lot of investment. Of the two parts of the administration's justification for canceling it, the first part is, of course, correct. Mars sample return is grossly over budget. It was scoped originally, I think, at $5 billion. It's now $11 billion and climbing. And Congress has shown signs that they're unwilling to fund it anymore, and that's independent of the new administration. Congress was balking at the price tag. But it wasn't going to cancel it. So this is new. NASA does not have a confirmed administrator yet. Jared Isaacman is not in his job officially through Congress. And so the decision hasn't yet been made, but it looks like it will be canceled. And indeed, the second part of the question is it's correct that Mars sample return is independent of the idea of sending astronauts to Mars and bringing back rocks, which is a vastly more expensive and time-consuming undertaking. So however much it costs to bring Mars samples back, that technology is pretty well tested, even though it's expensive. And the timeline, even if it stretches out a few years into the 2030s, is pretty much in hand. The issue of humans going to Mars and bringing back rocks is completely uncertain, and the price tag and timescales are much larger. So these things do not directly compete with each other at all.
The next question is from Georgia Paget, who would like to know if you can please explain polarization.
Sure. Electromagnetic waves, light, radio waves, gamma rays, all electromagnetic radiation is based on coupled electric and magnetic oscillations, where there's a 90-degree angle between the sinusoidal oscillation of the electric vector and the sinusoidal oscillation of the magnetic vector. And these are coupled oscillations. So there is a preferred plane, and in normal radiation, the orientation of that plane rotates or varies as the wave travels through space. If you impose a filter on light so as to only admit one orientation of that electric field oscillation, that is a polarization. So that would allow, so polarized filter only allows one orientation of the electric vector and not the orthogonal variation or orientation. And so that's how polarization is measured, that's how it's determined, and some natural sources of polarization exist. Most light in the universe is generated in a random enough way that there's no preferred orientation to the oscillations in the electrical vector. But in some cases, due to a strong magnetic field, for example, there is a preferred plane. And so polarized light in the universe is useful because it tells us something about particular astrophysics.
Excellent, thank you very much. The next question is from one of our live participants. Dennis Dubé would like to know if living under the surface of Mars could protect humans from both cosmic and solar radiation risks.
Definitely, and indeed NASA's already done some interesting reconnaissance where the orbiters and imaging have identified lava tubes, which are natural underground caverns, if you like, where there's a cap, so there's a rocky cap, sometimes thin enough to be translucent, but usually of significant thickness, and then an enormous evacuated cavern, which is just a lava tube, an early geological formation. Some of these are huge. These caverns or lava tubes can be hundreds of meters long and tens of meters high, so they're completely big enough for a colony or a Mars habitat. And yes, they're a natural way to do it because you don't have to spend all that extra effort and money and use extra materials to protect the habitat. It's already done. So living underground makes a lot of sense on Mars.
Excellent. All right, it is 10:56, and I know we have to leave just a bit early today. There are a ton of questions today that we have a lot of people with us, and I know we did not get to answer them all. And we want to thank you for being here and invite you to come back to our next session in 2 weeks. So I believe that is going to be on at the beginning of June, so I don't remember the exact date, but that will be early June. Please subscribe to our channel and click the bell icon so that you hear about upcoming live sessions. And if you go to our channel page and you click on the live tab, all of the upcoming live sessions are listed, and you can see the next one that will be happening. And so please come back and ask those questions that didn't get answered today. The next one is June 5th. So please come back and ask these questions again at our next session, and hopefully we can get to some more of these. And thank you all very much for joining us today. Please have a great rest of your week, and I'll let you say goodbye, Chris, and then we'll log off.
Okay, thank you all, and thanks to Matthew for running the session, and we'll see you in a couple of weeks.